Okay, dear students, so let us now find the energies of electron when they are orbiting around the nucleus. Let's see. So the topic here is energies, and we are going to find all the energies like potential energy, yes, kinetic energy, total energy, everything. First of all, let us try to find the potential energy of the electron when it is orbiting around the nucleus. This is very similar to what we did in the case of gravitation. Like, what is the energy of a satellite, like that. So let's say there is an electron here and the electron is moving. So the charge on electron is E and the charge on nucleus is given by ZE. Again, I'm not taking Z as 1, but we will substitute Z as 1 later. So from our knowledge from the topic D2, what is the expression for the potential energy in electrostatics? That is given by K times Q divided by R. And if one of the charge is negative, because this nucleus is positively charged, electron is negatively charged, so the potential energy expression will become negative for us. So I'm just taking negative sign here, so it will be given by negative this value. I'm not plugging in the value, like I'm not writing capital Q as ZE and all that. I'm just keeping it like this. Now, what about the kinetic energy? Kinetic energy will be given by half mv square. So now it is highly tempting. Find the expression for the velocity that we learned in the last video. Now plug in that in here. We're not going to do any of that kind of thing. Listen to this. So we're going for the easiest of the possible methods. So this is the centripetal force here. And I can just write that KQQ divided by R square, which is the Coulombic force. This is equal to mv square by R, that is the centripetal force. And like we did that in the earlier video also, but we are not going into like many steps or something. It's very simple and easy thing that we are going to do. R is cancelled here, so I want half mv square, so I'm multiplying half here and half here, so 2 in the denominator here and half is multiplied on the right hand side of the equation. So half mv square becomes kinetic energy, so we have the expression for kinetic energy already. So that is positive KQQ divided by 2R. Now, why is kinetic energy taken as positive? Because the charge is also negative. So why in this case, I'm not saying that kinetic energy will be negative. But in the case of potential energy, I said that because your electron is negatively charged, so potential energy is negative. Some students will be having that doubt. Listen to this. Kinetic energy is a scalar quantity, so it is never negative. So negative kinetic energy doesn't make any sense. So that is why kinetic energy is always positive, although the potential energy is also scalar, but still it is having negative values also, because infinite potential energy, sorry, the potential energy is becoming zero at infinite distance, and potential energy in the case of attractive forces is never positive. So it has to be taken negative. So here the potential energy is negative. And why is that? Because there is attraction force between these two. Why is that? Because one charge is negative, another charge is positive. So we can say because the charge is negative, the potential energy is also negative. Anyways, so potential energy is negative given by this expression KQQ by R. Kinetic energy is positive KQQ by 2R. Now I want to find the total energy, which is simple. It is the sum total of kinetic and potential. So a little bit of mathematics here. So this will be positive KQQ by 2R, negative KQQ by R. This is going to give you a value of negative energy, which is equal to kinetic energy in the magnitude. This is total energy. So this is our final expression for total energy. And you can see that total energy is negative. Now, of course, the next question becomes, what do you mean by that? Why the total energy is negative? This we have done in the topic D1 also when we were doing the satellite motion. Why is negative? This is called bound state. The bound state means that electron is bound with the nucleus. Electron cannot fly away. Whatever kinetic energy electron has, electron cannot fly away. Why the electron is not able to fly away? Because Like you can clearly see there is no string there. Like electron is not tied to the nucleus, literally. Even then, electron is tied. Even then, electron cannot move away. Why? Because there are Coulombic forces and all those things. This kind of a state is called the bound state from energy point of view. We have done the same thing in the topic D1, and I told you to remember these things. Now, in the bound state, what is the cornerstone condition for us? And that is given by this. Negative of potential energy is equal to the negative of total energy divided by 2. No, sorry. It's not divided by 2. The potential energy is divided by 2. This is equal to the positive of kinetic energy. This relation is a very peculiar, very important relation for us. This relation is known as bound state. Bound state, which is true in the case of satellite motion also, which is true in the case of atomic physics, in the case of electron also. So you can clearly see when I am going to plug in the value of total energy, kinetic energy, or potential energy in this equation, the equation is still valid. It is not invalid something, which clearly shows that electron here is enjoying the bound state. So this expression is very important. Sometimes kinetic energy of the electron will be given and you have to find the total energy. So you can just use the bound state concept and you can say it is just the negative of total energy. It is just the negative of kinetic energy. They are having the same magnitude. You can clearly see the magnitude of kinetic energy and total energy is same, but they have opposite nature. This is positive, this is negative. Potential energy, on the other hand, is same as that of the total energy, but it is multiplied by 2. So potential energy is having double the magnitude of the total energy. Bit ironic. It's difficult to understand why is that, but this is how it is. So this is called the bound state, and the total energy is given here. Clear? Now, there is a graph also which can be made for potential energy and kinetic energy. I'm just drawing it here. So graph is like this. You can say kinetic energy is always positive, and so it is having a hyperbolic variation which is shown like this. Potential energy, sorry, the total energy is just the mirror image of the kinetic energy, isn't it? But the total energy is negative and this is always positive. Potential energy is having double the magnitude of total energy, but it is always negative. So the potential energy expression will be somewhat like this. So this is potential energy, again this is always negative. So this is the potential energy. So you can be, you can draw this a bit more hyperbolic like this. So this is the expression for potential energy. Okay, and this is the radius r, this is energies. So this is the one part of energy that I showed you. The bound state concepts are valid in the case of electron and nucleus. But we are still not able to find that expression for kinetic energy that we were looking forward to. The expression which are similar to the radii, similar to the velocity expressions. Where is that? So we are now going to concentrate here. Let's see now how to do that. So total energy can be written as negative kqq divided by 2r, and I want to now plug in the values and find the expression earlier. So k is kept like this, q is ze, and the charge on electron is e, then it is 2, and then there is radius r. So I'm not plugging in the value of the radius r, so you have that very weird expression for the radius, which was there in the last video. You plug that value here, completely the same value. I'm not having that value written here, so I can't plug in that value here now. So you would be plugging this and you will find again a very weird and very big and scary expression for the total energy. In that expression, on a closer look, you will find all of the values are just constant and there is only one variable, which is n. So your final expression is coming out to be 13.6 divided by n square, and the unit is electron volt, it is not joule. This is the total energy of electron which is moving around in the orbit. What is the total energy? Total energy is given by 13.6 divided by n square ev, provided that we are talking about hydrogen and atomic number is taken as 1. So z value will be uh, substituted as 1. So this is the total energy value. Okay, dear students, so in this video, we have learned everything about energies. We have learned kinetic, potential, total energy. Then we learned about the bound state. And then we created an expression for ourselves. And this is the expression that you can use to literally find all the energies for all the shells in the case of hydrogen and all that. So that we will see in the next video. We would be talking about the energy level diagrams and the radius diagram also. So in the next video, we would be moving into deeper details, and they are very important for IB physics. Okay, dear students, thanks for watching. See you.